Okay, let's continue. Okay, let's look at this distance right here, CD distance. Alright, so this change of distance is 0.345. And this distance is exactly the length of the spring at the final position. Okay? So, the distance, or the change, okay, of length between the distance and the unstretched length, okay, for the spring, which is x1, x2, then becomes x1 originally, so that's the difference between the length, which is 0.555, minus 0.225. That's 0.33 meters. That's your x1. x2, final position. The difference between the two lengths is 0.345 minus unstretched length, 0.225, and that is 0.12 meters. So these two axes are what we're going to use in this work energy equation. Okay, expand this equation. Now, this first term, change in kinetic energy, is the sum of the two terms. The linear portion would have mv squared, v of the center of gravity, final position, square, plus 1/2 maximum inertia about center of gravity, omega 2, which is the unknown here, minus the whole thing, the initial position. Okay, it's a change of kinetic energy. Now, since initially everything is 0, it's not moving. Second term, change of potential energy due to weight, which is weight times delta z. Okay, the change of height. Okay, the change of height is this right here, this point G, okay, initially, and then finally the point G will move to this position, which is the same height as point B. Okay, so change of height is this right here, which is 0.45 minus 0.18, okay, which is 0.27 meters. Okay, so that's your change of height. So now it is further expanded and then plug numbers in. Okay. The velocity, okay, at point G right here, center of gravity. Can we relate this to omega? Well, from the equation, okay, V equals R omega. That's how you relate velocity and angular velocity. Okay, so velocity at point G, okay, which is this right here initially, okay, and then in the end, velocity at point G is here. Oh, except initially, this is 0. Okay, in the end, Vg has this position, okay, and the magnitude of it is related to omega, okay, by this equation. Okay, and R is the distance between this point G, okay, where my velocity is being applied, is being drawn, to the point of rotation, okay, which is point B. So this distance of interest here. Okay, so this distance then can be figured out, right? Because now this is 0.45. Okay, and so between G and B, actually I just figured out here, right? G and B, which is 0.5 minus 0.18. Okay, so same distance as here. Okay, so it's 0.27. So velocity then equals 0.27 times omega 2. Okay, so this becomes 1/2 m r omega 2 squared. Okay. And plus 1/2. Now, the mass per meter inertia for a slim rod, for a slender rod, about its center of gravity is given in the book, and it is 112 mL squared. L is the length of the rod, and then omega 2 squared, of course, that's the unknown. So unknown appears in these two terms. Okay, 0, nice, plus weight of the rod. Okay, weight is mg, m is given, okay, times the change of height. Okay, so that's called delta z now. Okay, just notice that I haven't plugged in the numbers. Okay, so I want to simplify and bring in all the individual terms before I can actually plug in each of the individual numbers. Okay, and then the spring term, 1/2 k, which is given, x2 down here, and x1 that's down there, 1 square 0. Okay, now I can bring in all the numbers, and you know all these now. Okay, m is 6, right? R, okay, just figure out to be this, right? So this is my R right there. Omega 2, that's the unknown. The unknown, so you group terms together, everything else has been figured out. So, plug in numbers and work through the math, punch into your calculators. Omega 2 turns out to be 5.44 radian per second. And it is obviously clockwise. And that will be it.